I would also like to welcome, say hello to students and professionals from Peru and Chile, as well as any neighboring countries, and acknowledge the sponsors, the organizers, of course, the sponsors, and the patrons of this series. I'm sure the students appreciate it very much, as do I. I'm glad to have this opportunity to talk about a topic that I'm interested in and is appropriate to the formation of ore deposits in Chile, Peru, and the whole Cordillera. Today's talk is exploration implications of 5 different formation environments for advanced argillic alteration. And for anyone who doesn't know what advanced argillic alteration is, I'll define it in a moment. But for example, here at Salares Norte, which is a recent discovery in northern Maricunga district of central Chile, there are 3 different styles of advanced argillic alteration formed in 3 different environments with different positions relative to the ore body. And it's important for us to understand these differences so that we can appropriately interpret the alteration mineralogy. So I'm going to discuss these details as we go along and use examples from ore deposits, mainly ore deposits in Chile and Peru that I have particularly worked on. So the first topic will be just a brief overview of the epithermal and porphyry environment that forms gold and copper deposits. Next, something brief on hydrothermal processes and how advanced argillic alteration forms. But as I said, these are 5 different geological and chemical environments. And I'll discuss the relationship to ore zones. And I'll be stressing throughout the talk the implications for exploration. And the bottom line, what we call the takeaway points of this talk, is it's important to determine the mineralogy, alteration mineralogy, including the textures of the rocks, the morphology, meaning the distribution, is it a flat-lying blanket or is it high angle, and the zoning of the minerals. Therefore, keep the mineralogy and don't use terms like advanced argillic alteration on our alteration maps or in logging. Keep the mineralogy. Well, first of all, what is the importance of the epithermal and porphyry environment? Porphyry, of course, Chileans as well as Peruvians will know the importance of porphyry. Over 70% of the world's copper is produced from porphyry copper deposits, formed in volcanic arc settings, either oceanic, like Philippines and Indonesia, or like in the Cordillera of the Americas, in a continental volcanic arc. Subduction of the plate beneath the margin of the continent. Epithermal is also in this environment related to the shallower levels of the porphyry. Epithermal can also be related in this back arc zone of extension. Now, however, in this back arc environment, there's not porphyry. This overall environment is also responsible for the formation of up to about 40% of the world's gold production, excluding placer deposits of South Africa. And so, very important environment of copper and gold mineralization And all of these environments can have advanced argillic alteration associated with them. And this includes the epithermal environments. For example, in the arcs, volcanic arcs, we have high and intermediate sulfidation styles of epithermal. And in the extensional zones, we have low sulfidation. That's another lecture. I won't discuss more details about styles of epithermal. A recent paper, 2010, by Richard Sillitoe, now very well distributed, talks about the porphyry copper system. And by porphyry copper system, Sillitoe didn't refer only to the porphyry copper deposit, but to all of the alteration in this whole intrusion-related environment. Deep potassic alteration, chlorite cerussite alteration, but also the advanced argillic lithocap. And this is a shallow, relatively shallow, upper maybe 500 meters or possibly a kilometer depth of advanced argillic alteration following a permeable lithology. Therefore, using the term lithocap, cap meaning it's sitting over the intrusions. And there's a variety of alteration we'll discuss in that lithocap. What about the ore deposits? Well, porphyry deposits, they are porphyry copper deposits. They are 1 to 2 kilometers deep, associated with the deep intrusions that intrude to 2-3 kilometers depth. There may be skarn if there is some type of carbonaceous rock, limestone, etc., skarn and carbonate replacement deposits. And then within the lithocap, we have high sulfidation deposits, epithermal deposits formed. And on the margins of the lithocap, there can be intermediate sulfidation deposits. Well, let's take a look now at the different advanced argillic alteration environments. Of course, a lot of the advanced argillic alteration forms in the epithermal environment, the upper 1 kilometer or so, but it can also form deeper, as we will see. So this is a recent diagram that we've created along with my colleague, Antonio Arribas, and it shows the 5 different environments of advanced argillic alteration. I'll define advanced argillic alteration in a moment, but right now, first, this is just an overview. Perlite is an advanced argillic mineral, and right at the tops of the porphyry or the base of the lithocap, we can have white mica, such as muscovite, in a transition to perlite. So there's very deep advanced argillic alteration here. Then what we call hypogene, hypogenica, acid sulfate and chloride. And that is what, that environment is what creates the advanced argillic lithocap. Then we have what's called steam heated acid sulfate. And that forms a blanket, this green horizon, a blanket over the tops of the ore bodies very near the Pelu surface. There's also steam heated CO2 or carbonic acid alteration. That's basically advanced argillic. And anyone who likes beer, cerveza, knows that the CO2 bubbling in the cerveza, that makes it relatively acidic, a pH of about 4. So even your beer is acidic, but that's due to the large amount of CO2 present. And finally, there's the superhenica, the post-ore mineral oxidation of pyrite in the atmosphere. This is afterwards, and this of course can overprint all of these environments. Okay, now something about epithermal. As I said, epithermal forms within about a kilometer. Epithermal veins and ore deposits form within about a kilometer. The red and blue are intermediate sulfidation, vertical ranges of ores below the paleosurface, here at 0 meters. This term was introduced by Valdemar Lindgren in 1922. He recognized that this is a special environment, first from his studies of epithermal deposits in the Western United States, but they're the same all over the world. And epi is Greek for over or above. So that's why he used the term epi, and thermal meaning temperature, over or above thermal waters in the upper kilometer. Well, we see that these veins, in the case of extension environments, low sulfidation veins, form very shallow depths, maybe up to the paleosurface. These other arc-hosted veins often are a few hundred meters depth. Now, if we have erosion, a few hundred meters of erosion below the paleosurface, the surface at the time of formation, then oftentimes we expose these epithermal deposits, and they are relatively easy to explore. Of course, if we have very deep erosion of a kilometer or so, basically we have eroded to the base of the epithermal deposits. And most of the epithermal potential is now gone. It's been eroded. In this case, however, it's possible that we actually have, we are closer to the porphyry environment if we've eroded the upper kilometer. So now we should be looking for porphyry copper potential. Finally, if there's very little erosion, less than 100 meters or so, then all of the epithermal potential is still remaining at depth. And so we should be able to, we have to be able to assess these different levels of erosion, and we can do that using alteration minerals, alteration mineralogy, as I'll discuss. So now this brief overview, let's talk about minerals in the Advanced Argillic Alteration group. The term was first introduced by Meyer and Hemley in 1967, and these minerals include alunite, alunita, and also kaolinita, dikita. The kaolinite and dikite are candite minerals or kaolin group minerals. They're aluminum silicates. Perlite and andalusite are also aluminum silicates. There's no potassium present or other cation. Diaspore is aluminum hydroxide. And then zunite and topaz, these are also aluminum silicates, but they have fluorine. So we know there was a lot of fluorine present, as well as chlorine. Back to alunite, this is an aluminum sulfate mineral with some potassium. And these are all the components that make up these minerals. And these are not the standard components. Many of them are not the standard components in alteration of, say, potassica alteration of biotite and potassium feldspar, or even phthalic alteration of white mica, muscovite or illite. We're looking at sulfate. We're looking at aluminum in solution, phosphate, hydroxyls, and fluorine. Well, these minerals form at relatively acid conditions, pH 2 to 4, more acid than even your beer. And one style of alteration called residual quartz with a vuggy texture, it forms even more acidic environment, pH of 1. This is actually not advanced argillic. This is considered to be an extreme leaching. And as I said, these occur at a shallow depth. That's why they're very important for epithermal exploration, but also they're important for exploring the tops of porphyries, because this alteration can extend below the epithermal environment a little bit. The perovskite that I mentioned in the first alteration type, that is advanced argillic alteration. Okay, a little bit of background now on this style of alteration. And in the early title, I used hydrolytic alteration. That simply means alteration by hydrogen ions. The hydrogen ion, remember the pH, the definition of pH, it's minus the logarithm of the activity of the hydrogen ion. Of the hydrogen ion. And so the more hydrogen we have in solution, the lower the pH. Now, just a few reactions just to show you the what's happening to produce advanced argillic alteration minerals. First of all, the alteration of K feldspar to white mica, either muscovite or illite, requires hydrogen ion. And this releases potassium to the solution. That is hydrogen metasomatism or hydrolytic alteration. Then, if we have more hydrogen and we alter white mica, muscovite, with the hydrogen ion, this will go to kaolinite, a kaolin mineral, plus potassium, more potassium released to solution. If we take and add even more hydrogen, 2 hydrogens to white mica, we can form perovskite. We need some silica here, but we form perovskite. And if we take kaolinite or dicite, candite minerals, and we add a large amount of hydrogen ion, then we simply leave quartz, a residue of silica left in the rock, and even the aluminum that was present in, oops, that's odd, even the aluminum present in the kaolinite has been released to solution. So advanced hydrolytic is basically advanced argillic by definition. So where does the hydrogen come from? Because obviously we need hydrogen ions to create these advanced argillic alteration minerals. So let's look at the 5 environments for generating high hydrogen. Starting with El Salvador porphyry in central Chile. It was discovered in the 1950s. There were very few roads into this area. It was, in fact, you could only reach this area by a railroad. And there was a large area of muscovite present at the surface. And more recently, we mapped the area because this porphyry deposit was discovered so quickly, drilling up in this area, that they didn't have complete maps of the surface alteration. They were very fortunate to discover this porphyry very early. But you notice that in this upper area at the top of Indio Muerto, the sort of buff brown color is perovskite replacing muscovite. Why do we see this perovskite with muscovite? Let me move my photos here. Well, because as this, I'm going to have to minimize this. Okay, As the fluids are cooling, muscovite stable, also maybe a little bit of andalusite, on cooling, simple cooling, they went into peroxide stability. And so, simple fluid cooling caused the muscovite to shift to peroxide stability, and further cooling actually can result in dicite stability. And so, although the potassium to hydrogen ratio is constant, in fact, what's happening is that the stability fields of these minerals are changing, both in terms of temperature, peroxide and then dicite becoming stable at lower temperatures, but also at different potassium over hydrogen ratios. Here we see the muscovite plus andalusite zone at the summit, near the summit of Indomuerto, being replaced by peroxide. That's simply related to the late cooling. And the reaction, as I already showed, was the muscovite with 2 hydrogen ions going to peroxide. Now, this is a oblique cross-section, meaning we're sort of looking down onto El Salvador to the southeast, but then we've cut through right here. So this line is the surface, and this shows the depression, and then this is cross-section down. This is from Gustafson and Hunt. It looks like I didn't get that on quite on the slide. Now, first of all, we see that there is an area of muscovite and andalusite alteration outcropping at the surface, along with oxidized pyrite bornite chalcopyrite. These were all supergene oxidized, so we don't see them at the surface, only where they're encapsulated in quartz veins. But when we look in cross-section, we see that at depth, around the latest intrusion, we have a zone of bornite chalcopyrite and chalcopyrite plus pyrite. This is the ore zone that's being block caved at El Salvador. Subsequently, as the fluids are cooling, this is the zone of peroxide, and you can see how it very well matches the distribution of the muscovite, except that muscovite is much wider in distribution, whereas the peroxide is proximal over the top of the porphyry copper ore body. So in this case, knowing that this peroxide could be related to the proximal or near portion of the deposit over the top of the porphyry deposit would help an explorer to focus on this area, exploration of this area. So that's one of the first lessons. Okay, the next, change that a little bit. The next environment, number 2, is hypogene magmatic vapor condensation that forms very acid condensates. Acid condensates, but barren. Now, this is a rhyolite dome, 1,000 years ago it was extruded just south of Kyushu in Japan called Satsuma-Iwajima. These are acid hot springs along the margin, pH 1.5 acid springs. And you can see these precipitates around the island. These are actually dissolved rhyolite. Rhyolite dissolved into these acid fluids. And what the leaching does is it leaves behind this residual quartz. And the residual quartz has a fine buggy texture after the original rhyolite. So this is 97% silica near the summit with alunite and some clay minerals, but only up to 29 parts per billion gold. Anomalous, but of course not at all, no potential for economic interest. But that's because at this stage, the residual quartz and the quartz alunite are still barren. But it does tell us that there's a magmatic system at depth. Maybe that magmatic system is related to a deeper high sulfidation epithermal deposit that is hosted by this type of alteration, or even at greater depths, it's related to a porphyry deposit. And in fact, the same alteration, we see the same alteration in high sulfidation epithermal ore deposits, such as Summitville in Colorado. Here's the residual buggy quartz. You can see these 2 centimeter size pelagic clays, phenocrysts, phenocrystales de orthoclase. And here the same scale, but the orthoclase is still present, altered to alunite. So this would have been a pH 2 to 4, but here we have pH less than 2, and so even the alunite was dissolved. Now this is the environment that these styles of this acid fluid forms in. These are the reactions. We have magmatic SO2 and HCl. The SO2 combines with water to form sulfuric acid, H2SO4. And then both H2SO4 and HCl, on cooling, those acids start to dissociate. And so they release their hydrogen. And it's that hydrogen that causes the very acid conditions is as low as pH less than 1. And in those cases, aluminum is soluble, and we're left with residual, residual quartz in the core zone where the fluids are most acid, and then where they're less acid, pH greater than 2, then we have a halo of quartz alunite. And here is Satsuma-Ujima, about 20 kilometers to the south. Just in southern Kyushu, there are ore deposits such as Iwato, high sulfidation deposit, in what's called the Nansatsu district of southern Kyushu. And here we have quartz alunite alteration that was formed about 3 million years ago. So the same type of volcanic and acid hot spring activity here today at Satsuma-Ujima was occurring 3 million years ago on the island of Kyushu. This is a view of the lithocap-hosted Iwato high sulfidation deposit. As we can see, all the sulfides have been supergene oxidized. We have this reddish brown iron hydroxides present. So that means the 3 to 4 grams per ton gold is released, very easy to recover. Now the gold is hosted within the residual vuggy quartz, greater than 1 gram per ton, whereas there are very sharp contacts with zones of alunite. For example, here we have, you can see, you can put your hand on that contact. It's so sharp. The residual quartz formed at pH less than 2, whereas the alunite stable at a pH of greater than 2. We'll just, yeah. And what else did I want to point out? Yeah. So the same environment that we're witnessing today formed these deposits. They leached the rock, and then after leaching, gold was introduced. This is I say recent discovery. It's now 20 years old, but a discovery in southern Peru in the Arantani district. And it's an ore deposit called Tucari. This is Tucari right here. It outcrops the top at 5,240 meters, which is one reason why it was not discovered until only 20 years ago. There were no roads into the area, and it took some effort to come in by horses to first find and then sample this outcrop. And this is all residual quartz. And this was found in an old ore district of lead, zinc, silver veins. These were actually intermediate sulfidation veins. You remember our early schematic? We had lithocap with high sulfidation, hosting high sulfidation deposits, and on the margins were intermediate sulfidation veins. Same in this case. This shows from the opposite direction the residual quartz of Tucari, surrounded by quartz alunite and quartz dicite alteration. And let's take a look at a cross section here. We have the Barroso andesite volcanic rocks, but what was important to formation of the residual quartz was the later intrusion of this porphyritic dacite. That brought with it the hydrothermal fluids that first leached the rock, the dacite, and the andesite, and then subsequently introduced the gold mineralization. This is the alteration. We can see within the core of the deposit, associated largely with that dacite intrusion, there is residual quartz and also zones of massive quartz with a halo in the orange of quartz alunite advanced argillic alteration. Well, this leads us then to a simple schematic for this style of alteration. I will move this to, yeah. And that was that there's a deep magma associated with the formation of this style of magma of alteration. It produces the SO2 and HCl vapors that eventually condense. It forms along the structural feeder zone, it forms residual quartz, sometimes vuggy, with halos of quartz alunite alteration. If there is a horizon, a permeable horizon, it's possible for this alteration to flare or to mushroom into the permeable horizon and cause the lithocap alteration. Subsequently, then, and I should say that many lithocaps are barren. It's only the vapor condensates that create the alteration, but there's no mineralization. That's because the mineralization comes after the alteration. But where there is mineralization, it's focused within this feeder zone and in a proximal area close to the feeder zone relative to the lithocap. So if you're exploring this distal part of the lithocap, you have to understand the zonation that will get you closer, point you closer to the direction of the feeder zone. Now, this brings us to steam-heated alteration, the third style of alteration. I've talked about quartz alunite alteration. Also, there's kaolinite dicite alteration in the lithocap. Well, there's also kaolinite and alunite in steam-heated zones, and those form above the groundwater table in the same environment. Now, remember, HCl and SO2 are responsible for forming the hypogene, advanced argillic alteration, very acid condensates. But in the same environment, the same volcanic environment that we see here at White Island in New Zealand, we can also have low temperature fumaroles with only CO2 and H2S. And where the H2S condenses, then it can also oxidize to sulfuric acid. This is the process. H2S that is lost from the deep liquid that's boiling, brought to the surface. It brought to the surface by vapor, 100-degree vapor. The atmospheric oxygen oxidizes the H2S to sulfuric acid in the vapor zone, or the unsaturated zone above the groundwater table. This between the surface and the groundwater table, that's the zone where the condensate forms and the oxygen can oxidize the H2S to sulfuric acid, forming a pH typically about 2 to 3. And therefore, these tend to be alteration horizons because groundwater tables are also horizons. The alteration forms above the groundwater table. Here we see some of these acid mud pools, kilnite forming mud pools in Wairaki, New Zealand. Here's where these vapors are discharging, and sometimes we get shallow eruptions forming craters. This is where the H2S is oxidizing to sulfuric acid. And this is a bubbling, CO2-rich bubbling acid sulfate pool in Yellowstone, which I visited last year. I have a short video here. I'll try to play it. This is not boiling, this is bubbling of CO2. So the pH of this spring is about 2.5. The temperature is about 70 degrees. So it's not boiling, it's bubbling. And it's bubbling because of CO2 loss to the atmosphere. And these brown clays here are dominantly kilnite. Now that's forming above the groundwater table. This is forming our blanket of steam heated acid sulfate alteration of kaolinite, sometimes alunite. And coming back to South America, here is La Coipa, which is just near to the east of Copiapó, near the Maricunga district, and it's produced a large amount of silver and gold, 150 tons gold equivalent, but mainly silver rich. And that was the number in 2005. But so this is residual quartz hosting the gold mineralization at depth, but over the top, this is the residual quartz. We can see some vuggy texture. There's even some native sulfur left. But over the top of the residual quartz is steam heated alunite kiln blanket with some chalcedony. So that was the steam heated alteration over the hypogene, very acidic alteration, formed in the same, very similar environment. Now, if we go 4 kilometers to the northeast from La Coipa, we come to an area known as Puren. Puren has had very little erosion. And so there's only, at the surface, there's only steam heated kaolin alteration. And in addition, we also see at the base of the kaolin alteration, we see that there's a chalcedony blanket. That chalcedony blanket, or opal, forms at the paleo groundwater table just below the steam heated alteration. Do I have? Yes, I do have a photograph of the opal. We can see this opaline conchoidal fracture. Opal fractures conchoidally, just like glass. And so that's how we recognize this opaline silicification, distinguish it from residual quartz, which shows bugs, etc., the original rock texture. Here, this is simply silicification along the tooth horizon. Now, a couple companies drilled this area, Purinsur. The 12 holes that were drilled were not successful, but then they followed some geochemical, geophysical anomalies to Purin Norte. They drilled, and fortunately, they found the Purin ore deposit. Below, a thick horizon of steam-heated alteration with keelnite, also opal within this horizon. And we can see that it's about 30 meters thick, essentially barren. You can have at the base up to about 3 ppm silver, but very, very low concentrations of indicator elements. Below the deposit is the Purin deposit. Here we see this blanket in blue of steam-heated alteration. It's a horizon. Again, remember, it's related to the paleo groundwater table. That's why it's relatively flat. And it sits over, as a blanket over the ore body. In this case, we're looking at quartz ore body and halos of illite alteration. And the silver is dominantly hosted by this silicification, overlaying by the steam-heated keelnite opal blanket. So our third environment of steam-heated of advanced argillic alteration. Now, some people may have traveled to Wyoming in the US, to Yellowstone. This is the area that made Yellowstone famous, the Grand Canyon of Yellowstone, with many, many different colors of whites and yellows and reds. Well, what caused these colors? This is steam-heated keelnite in through here. And here we see that this keelnite has horizons of groundwater table opal. This is an opal horizon right here, silicification, thick sequence of keelnite. And the reason for this thick zone of keelnite is because the Yellowstone River has been eroding downwards while the hydrothermal system is active. There are hot springs forming silica sinter down in this stream valley, river valley, and therefore the illite and pyrite alteration at depth that was formed below the steam-heated alteration now is being eroded, and as a result, the pyrite related to the illite alteration is altering to iron hydroxides. So the steam-heated alteration, the deeper pyrite, illite pyrite alteration that's been supergene oxidized, that caused the wide range of colors in this valley exposed by the river erosion, and that's the reason that Yellowstone was turned into a national park. Here we show from a recent study by Larson, 2009, originally, a few 100,000 years ago, there was silica sinter at the surface and a horizon of keelnite over the hydrothermal system, but the river started to erode, and as a result, the groundwater table then lowered as the erosion continued. And now, today, we have the river erosion as much as 300 meters here, hot springs in the bottom of the river valley, but with a very thick extent of keelnite alteration with silica sinters and opaline horizons left behind at higher levels. So it might be confusing at first when you look at it, but that's why, because of this thin hydrothermal erosion. And we see that elsewhere. For example, this is Pascua Lama in Chile, Argentina, along the frontier. extensive areas of steam-heated alteration formed at the time of the Pasqua deposit, and then subsequent erosion and deeper supergene oxidation of deeper sulfides below the steam-heated alteration. So this occurs in many environments around the world. Okay, that's steam-heated. I've talked now about the three more important environments. Steam-heated CO2-rich does occur. I'll only talk about it briefly because it forms kelnite. Actually, we sometimes call this argillic alteration, but some people are confused, and because of the kelnite, they also call it advanced argillic. It forms with clays. And as I mentioned, it forms because of CO2 combining with water, forming carbonic acid, creating pH of about 4.5. And this is what causes the acidity of the beer that you drink, maybe this afternoon to celebrate your end of year seminar. And let's take a look at an active geothermal system here in the back arc environment of New Zealand. This is the Broadlands Oahu geothermal system with geothermal wells discharging here. And right here is a silica-sintered boiling hot spring. If we take a look at a cross-section, we see the measured temperatures. This is the zone of upflow, 275 degrees at less than a kilometer depth. So this area is boiling, and we get adularia depositing as well as illite clays at temperatures above 200 degrees. And at lower temperatures, we get illite smectite, interstratified, or smectite clays stable at lower temperatures. However, also on the margins of the system are where CO2 condense. And that's when we can get deeper kelnite, or in this case, iron carbonate, siderite, forming as well. So this is not steam-heated acid sulfate alteration. That stays right at the surface. This is actually related to CO2 in vapor condensing below the groundwater table. This is one well, number 6, that discharged a CO2-rich froth, just like opening a can of beer that was maybe warm and it bubbles all over. The CO2 is what's bubbling out. And if you leave your can of beer out overnight, the CO2 will be lost and the pH will go up and it'll taste different the next day. So where does this occur? Well, here in northeast Russia, we have a deposit, Kupol, discovered in about 18 years ago. No, 1996, right, by Slava Zagorsky. And this shows the andesite, residual andesite, which was called dome, meaning Kupol in Russian. And there's a big vein that outcrops at the surface with beautiful colorform textures, typical low sulfidation epithermal vein. Now, it outcropped at the surface with very high grades of gold, up to 20 grams per ton. This long section also shows the high grades of silver. But to the north, we see that the gold and silver has been offset to greater depths. And that's due to a fault, down-faulted part of the northern extent of the vein. And we see this also in the alteration mineralogy with the chlorite and illite associated with the main ore body, down-faulted to the north, and at shallower levels, this zone of smectite, lower temperature smectite alteration. Well, if we look at a cross-section right here, we see that the vein has its halo of chlorite, illite chloride alteration formed at higher temperatures. And at shallower depths is this zone of illite only, or illite plus kaolinite. Now, this illite plus kaolinite probably formed from those CO2-rich condensates on the deep margin of the system. So we should not think that this kaolinite was related to descent of acid sulfate steam-heated waters. It was actually related to carbonic acid waters on the deep margins. So another environment to remember when we're interpreting our alteration mineralogy. Finally, supergene weathering of sulfides. This occurs after alteration. Here we have principally pyrite being oxidized by atmospheric oxygen going to sulfuric acid and iron hydroxides. The pH can be very low, less than 2, less than 1, even less than 0. And it results in sulfides oxidizing at the surface. For example, here at Rodicular in Spain, Almeria, a high sulfidation deposit in Spain. And also, as I pointed out, similarly in the Pascualama deposit, large amounts of supergene oxidation, and at Yellowstone, Grand Canyon, an active geothermal system, even now starting to have supergene oxidation. And here, the alunite often is forming in fractures, but because it forms at low temperatures, it has very, very fine crystals, muy fino cristales, in these fractures, as opposed to the large alunite crystals that form in higher temperature, hypogene, lithocap situations. So very blocky alunite formed here in the supergene environment, plus, of course, iron hydroxides. We don't get iron hydroxides formed during hypogene or even steam-heated alteration, but we do form them during supergene alteration. And this style of alteration, this style of oxidation, of course, is very important to economics because it breaks down the refractory pyrite. Now, one last example before I finish up. I see that we're coming close to 10:30 in Lima. 11:30 in Concepcion, should finish in about 5 minutes, and we can open to questions and discussion. Here, again, back to the Maricunga district, northern Maricunga district, Goldfields a few years ago discovered the Salares Norte deposit, and by 2018, they had 3.5 million ounces of gold in indicated resource, mostly having been supergene oxidized. But there are 3 types of alteration here. Excuse me. And here we see Aster Alteration Map of the area. There's a dacite dome here with alunite and kaolinite in orange and yellows, and also steam-heated opaline silica in the blue. And this is right where the Salares Norte deposit was discovered, right next to this dacite dome. And here we see the alteration section. There's 3 styles of alteration here. One is hypogene, quartz alunite, residual quartz and quartz alunite formed at high temperatures associated with this diatreme. Right through here, that breaks through to the present day surface. This has been then overprinted by a second style of alteration, steam-heated acid sulfate, with both steam-heated alteration at the surface. We could see the dome next to, in the photograph, next to Salares Norte, and also steam-heated related chalcedony as deep as 100 meters or more below the present-day surface, right at the lowest part of the groundwater table. And then later on, all of this was overprinted by supergene oxidation. And the pyrite was completely supergene oxidized with, as I noted, 95% of the ore body now having been supergene oxidized. So there are three types of kearnite and alunite: hypogene, related to the ore body, steam heated over the top of the ore body, and later supergene alteration. Three styles, they're overprinting each other. With the ore stopping right at the top or right at the base of the paleo groundwater table. All of the ore is below the paleo groundwater table as defined by the steam heated alteration, similar to Perrin, which was the exploration model for goldfields to use when they're exploring for Salares Norte in this area of extensive steam heated alteration, as well as supergene alteration at the surface. So, three origins of advanced argillic minerals, but a lot of overprinting. So important to report the minerals and the textures. With both kearnite and jarosite being steam heated as well as supergene in origin in this area. Now, one last detail, we haven't talked about it, but the advanced argillic alteration minerals formed at acid pHs, many of these minerals have different temperatures of stability. And so they help us, when we recognize the minerals, to identify whether or not we're in a low temperature zone that was distal or a higher temperature alteration zone that was proximal, such as perovskite and diaspore, or even dicite. These are proximity indicators, particularly in hypogene alteration. So it's important to keep the mineralogy rather than just calling it all advanced argillic alteration, because we see we have 5 environments: the transition from top of a porphyry to perovskite alteration, the hypogene lithocap environment, CO2 rich on the margins of veins, steam heated zones at paleo groundwater tables, and then supergene overprint at low temperatures. So finally, we just, of course, repeat this, that high temperatures here, right over the top of the porphyry, but base of the lithocap. The lithocap associated with the hypogene acid sulfate chloride fluids formed from volcanic vapor condensates, subsequently mineralized in some cases, but remember, this alteration style is barren on formation. Oops, the steam heated styles of alteration, steam heated acid sulfate over the paleo groundwater table where we have oxygen, whereas where we are below the groundwater table, then they are carbonic acid rich, and finally, post-mineral supergene oxidation. So I think with that, just final comment, when you're mapping or logging, don't summarize, don't call it advanced argillic alteration, because we're losing all of these details. Look at the mineralogy, the textures, and the morphology to help to define what is the environment of that alteration mineralogy. How can it help direct us towards the potential ore body, whether it's high sulfidation epithermal, intermediate sulfidation epithermal veins, or possibly even deeper porphyry environment. Well, with that, Carolina and Carlo, I'll finish and open the talk to any discussion or questions that people may have. Thank you.
Thanks, Mr. Hedenquist. Well, we had questions.
Yep.
The first is by Thomas Lizana. What
Yep.
is the importance of Variate in epithermal systems?
Which chloride?
What is the importance of Variate in epithermal systems?
Barite. Sorry, my hearing wasn't so good. Very good point. Notice that in this in here I didn't include. Did I? Is Variate there? No. Actually, I should add barite. Thank you for that point, because barite is a barium sulfate mineral, and obviously it needs sulfate to form. Oh, sorry. Let's see, I'm trying to move the pictures. It needs, no, I didn't include here. It needs sulfate to form. So it can form in acid conditions, but also fairly neutral conditions in through here. And importantly, it commonly comes in the later stages of alteration. The person who answered it may be familiar with barite at El Tambo, at El Indio, or maybe barite in some of the deposits in Peru, where it's associated with some of the ore minerals. It's a later stage sulfate that for me is very positive. It seems to come with the ore minerals. It's not just formed in the early alteration stages, but it's also introduced with the ore minerals in relatively oxidized conditions. So it's quite common in high sulfidation deposits and sometimes even in intermediate sulfidation, but not in low sulfidation, because low sulfidation is formed in more reduced conditions, so we don't have sulfate. Thank you for pointing that out, and I need to add barite to this diagram.
Okay. The second question is from Monica Alba, and she asks, what indicates molybdenum anomalies in HS, or high sulfidation epithermal, I guess?
Yeah, well, molybdenite in high sulfidation. Well, of course, we know that we are at, if we're in high sulfidation, we know we're in the porphyry environment. Doesn't mean porphyry ore deposit, but at least shallow intrusions at depth, possible porphyry ore environment, possibly copper and molybdenum. And in high sulfidation deposits, I have seen molybdenum sometimes up to 0.1% anomalies of molybdenum. So it can be very high, whereas there are other deposits, such as in the Nansatsu district of Japan that I pointed out, Iwato, one of the deposits, it's only present at about, a few tens, 20, 50 ppm moly. So that's a good question, but one I cannot answer. Why is molybdenum, very high in some high sulfidation deposits, but low in others? So it points out that we have to be careful. We cannot use a recipe and say these 10 elements are going to be anomalous exploring for high sulfidation, because sometimes they're not all anomalous. So that's why we need, when we go to a new district, we need to collect samples of any mineralized material we can find, old mine dumps, etc., and find out what elements are anomalous and what elements are that we might expect are not so anomalous. Things like arsenic antimony, also molybdenum, etc. So that's the only answer I have to that, that there's variability, but I do not understand why there's all this variability in molybdenum.
Okay, Mr. Hedenquist, the next question is by Francisco Muñoz. He says, thanks, Professor. It is the climate an important factor to steam heated development?
Sorry, I missed the first couple words. Is what important for steam heated?
To steam heated development.
But what were the first words?
It is the climate an important factor to
Oh.
steam heat development?
Climate, yes? Climat?
Yes, climate.
Yeah, okay. Oh, good, another good question. Absolutely. Because, let's see, how about if I go back here? Steam heated. What's a good steam heated zone? What would be the good example? Well, why not Puren? And I'll just leave it like this for the time being. Now, I've said that to condense, well, let's go back and just, how about if we go back and replay this? I keep having to move the photos. Let's see. Steam heated acid sulfate alteration and mudflows. Now, clearly this mud pool is hot. It's not boiling, as I said, it's with CO2 bubbles, but it's still 70 degrees or so. So the temperature, high temperature, is related to the vapor. But most of this water here is groundwater, is rainwater. We need the rainwater in the groundwater horizon to condense the vapor. And if there's no rainwater, then there's not going to be that groundwater component, or it might be very, very deep. And so conceptually, you know, we can think that if there's no, for example, in the Atacama, if there's no rainfall at all, we might expect to have very little groundwater and therefore very little condenser to condense that vapor. And so perhaps in those cases, we'll form relatively little condensate. Whereas in some situations where there's a lot of groundwater, we may condense all of the vapor and form steam heated waters. Now, if the area is very low relief, flat, then there's not much of a groundwater gradient, not much of lateral flow, and we can get a lot of vapor condensation and develop high sulfate concentrations and therefore low pH. Whereas if we have a high relief, then it's possible that there's a lot of groundwater coming over, and as soon as it gets steam heated, it moves on. So in those cases of high relief, there also may not be as much steam heated alteration because the groundwaters do not develop very high sulfate concentrations. So yes, climate, I think, is very important, but also so is the relief and the gradient on the groundwater table. These are all factors to think about. Good point.
Thank you, Mr. Jeffrey. The next question is by Engineer Celso Palacios from the GAGEOQ consulting firm, the one that provided us kindly with this platform to carry out our first stage of conferences. He says, "Hi Jeff, this is Celso Palacios. Nice to see you again. Thanks for being here, sharing your knowledge. I have a question. In the last 5 years, how many exploration successful events have you realized worldwide after drilling barren lithocaps, parentheses, no gold, or blanket steam heated targets?"
Well, I don't know how many in total. First of all, yes, a good point for discussion, maybe over a beer with carbonic acid in it. Celso, it's been a long time since we've gotten together. And of course, also thank you for your support of this symposium. I don't know how many worldwide, but in my experience, for example, one would be, well, two, I should say. They're not the last 5 years. Puren, that was in about, what, 2000 discovered. But then Salares Norte was in, when was that? About 2013. I can look at my notes. I was there when the discovery hole was being drilled. I think it was 2013. And probably discovery was announced by 2013-14. At Salares Norte, about 600 talus fine samples were collected. And do I have it hidden here? I think I may have taken, no, I have it here. I don't have the numbers, but within the talus fines called here soils, all, let's see, there was less than 24 parts per billion gold in the talus fine samples. I think there were 500 or 600 samples, except one sample of 0.6 grams. And in fact, that one sample of 0.6 grams was, I think, related to a pre-mineral banded quartz vein in the fragments of the hydrothermal breccia, not related to Salares Norte brecciation. It was fortuitous. But the company would have drilled this area even if it hadn't been for that one single sample. And all the rock chips in the area, less than 35 ppb. So they put together all of the observations, and then they decided to drill. It wasn't because of one anomaly by any means. Chico Azevedo and Nate Brewer, they understood the barren steam-heated alteration from the studies at Puren Norte. That, for example, Antonio Rivas presented in 2005. And I mentioned that there was, let's see, do I have that at, where was, yeah, sorry about this. Yeah, I don't have the number here, but Antonio Rivas, he said that there was a 3 part per million silver anomaly in the steam heated zone. But if you look at his slides, that's in the base of the steam heated zone, not at the surface, the present day surface. And those 3 ppm silver anomalies, base of silver or steam heated zone, is related to the overprint of the steam heated alteration. Because at first, steam heated alteration was present at shallower levels with the 3 ppm gold anomaly related to the upflow from the deeper ore body. So you have to understand, as Goldfields did, and many other people now do, Placid Dome in these days, understand that you can have steam-heated alteration totally barren in gold, silver, arsenic antimony, etc., possibly anomalous in mercury, because mercury is volatile, but you can have barren mineralization. And let's see, I'm telling you, yeah. You know, we go back to Raymond Janis when he was exploring the Pascua deposit. This is pre-Pascua days. What was it called? Those days, I forget the name of it. But all of the steam-heated alteration, no one thought to analyze those rocks. He analyzed the area below the steam, just below the steam-heated alteration, and found gold mineralization at the present-day surface at Pascua. That was another example of, you know, getting, of thinking that the steam-heated alteration was not important. You had to drill elsewhere. So good point. I can't answer your question completely. I haven't worked on all of the discoveries, unfortunately.
Okay,
Any other
Mr.
questions?
Head.
Do we have any time left for more questions, discussion?
Yes, we have more questions. Daniel Higgins says, excellent presentation, thanks. In high sulfidation system, what field evidence should we find to determine that that system is eroded and mineralization has gone?
Yes, well, yeah, good point, because here we may, let's see, yeah, we may, well, let's take a look at this. Here at Tucari, obviously we have a large, this is about 600-meter long, 200-meter wide residual quartz zone, flared. But you can see if there had been 200 meters or 250 meters more erosion here, and this area had been eliminated, we would have been just in narrow, we would have had narrow zones, structurally controlled zones of residual quartz with extensive quartz alunite. And you know, that would have been good examples of maybe the lithocap level having been eroded. Or alternatively, maybe there was never permeability to begin with. But in this case, these structurally controlled zones would still be anomalous, 0.25, 0.5 ppm gold, maybe higher, but clearly only structurally controlled. So map the alteration, the mineralogy, residual quartz, vuggy quartz, as well as the alteration, and see if you're only left with these structures. Now, of course, if the structures are the only part of the system left, but if they're high grade, it may still be have potential. For example, El Indio, these structures contained 200, an average of 200 grams per ton gold. Those were the direct shipping ores. So even though they were narrow, they were high grade. So test these structures to find out how high grade they are, even if you don't have the larger lithocap, even if it's never formed or even if it's been eroded. That's a very practical exploration-oriented question, assessment question. Good.
Yes, Mr. Jeffrey, we're a bit running out of time, but we have 7 minutes left.
Yeah.
And well, there's a lot of questions left in the chat box too.
Well, you can send me some of the questions, and I can send you the answers. You can post them later.
Okay,
up to you. But
is
one
it
last
fine? Then, is it fine if we read one more?
Yes, one last question, and then we can turn on for Professor Ramos. I don't want to take any of Professor Ramos's time.
Yeah, sure. Last question from Rodrigo Hurtado. He says, first of all, thank you for the excellent presentation, Dr. Hedenquist. Regarding the hydrothermal andesite, in what scenarios can we find both hydrothermal and metamorphic, parentheses, contact metamorphism, andesite? How can we differentiate their respective origin?
Yeah, well, first of all, metamorphic andesite, when it forms in high-grade terrain, such as in Finland and Sweden, it is commonly formed from aluminosilicates like kehlnite or dicite, or even porphyry. And then it's very extensive, but we have schistose nature of the rock very commonly, and that andesite is pervasive. Whereas hydrothermal andesite is commonly altering specific phenocryst minerals, and is coexisting typically with muscovite, maybe being overprinted by diaspora porphyry. So look at the textures. I have never seen a situation where we have both hydrothermal andesite and overprint of metamorphic andalusite. I would say it's either one or the other, but I've never studied, say, metamorphosed porphyry deposits. So I would think it's mainly one or the other. And look at the textures, the overall textures of rock. Is there a metamorphic texture in the area? Is the andalusite pervasive, or is it present in phenocryst with these other minerals? Okay.
Mr. Hedenquist, we had a commentary by Victor Ramos. He said, "It is a great honor to talk after Professor Jeff Hedenquist."
Well, and please, Victor Ramos, thank you for the comment. And all I say is that I was the introductory act to start off for your presentation. And I'm going to stay and listen to what you have to say in Espanol. I will try to improve my listening capability. So thank you very much to all of the students, other attendees who listened, Celso Plachas and his colleagues for having sponsored the presentation, the Zoom presentation. And I look forward to Professor Ramos's presentation. Thank you.
Dr. Jeffrey, Carolina, adelante.
Okay. The both of the organization, we are grateful with you for accepting our invitation. Thank you so much for your time, and we hope see you again, maybe face to face in Peru or Chile.
I'm sure. Ciao.
Again, very grateful, and thank you for your willingness to participate of our stage. And if you don't mind a sec, le pedimos a todos los participantes si pueden abrir sus micrófonos para darle un aplauso, ¿cierto?, a nuestro ponente del día de hoy. A la cuenta de 3. 3, 2, 1, vamos.
Great presentation.
Gracias.
Gracias.